Okay, good afternoon, everyone. So first thing first, I have to appear in a meeting at 12:45, so I'll take 45 minutes of lecture today. Okay. You guys are in an AC room. Come on, it can't be that bad. All right. Uh, so any questions from the networking networking chapter? Any questions from there? No questions? Okay. All right. So I'll start the new topic, uh, and that's basically called device driver. The question is, what is the device driver, right? And why do we need one? So all the devices that we use on the system, right, requires to be operated, right? So you have the hardware device, like for example, you have the disk drive. You have to format the disk drive, and then the data is stored in a particular format, right? You have the network devices on your system, Ethernet port. You need to be able to, use that hardware. So there has to be some software running as part of your operating system that will communicate to that hardware to take the work done from that hardware, right? So that is the basic idea behind the device driver. So the device driver is the software which will run, or which will make use of the hardware, right? So let me just zoom this a little bit. So this is what we know, system call interface, and this is what we as a user or a programmer use. Okay, so whatever calls that we have made, whether it is open call, read write call, pipe call, fork call, whatever calls that we have made, they all belong to the system call interface. Okay, now the system call interface interacts with the kernel module, right? And these are all the kernel modules we have. Okay, so kernel subsystems are basically the systems which are taking help from each of the hardware devices that you have on the system. So for example, you have the process management system, which will implement concurrency and multitasking because you have multiple cores in your system, right? So you have multiple CPUs, multiple cores in your system. To take an advantage of that, your kernel module process management needs to implement concurrency, multitasking, locking mechanism, all of that, right? And that also has to be done using the architecture dependent code. So why it is an architecture dependent code is because, let's say on my laptop, I may be using Intel based processor. On your phone, or maybe on Apple Mac, you would be using ARM based processor, right? So that is what we are saying, architecture dependent code. Okay. Then you have the memory management, right, that you have to perform, where one of the important concept is called virtual memory. What does virtual memory do? So basically what happens is that most of the computer today, general purpose computer, which we call desktop laptops, they come with like 8 GB, 16 GB of RAM, right? But the data that you really need to put in RAM is much larger than that. Okay. So what happens is that the kernel module, which is managing the memory management, it creates what we call virtual pages or virtual memory in your disk. Okay. And there will be a special routine which does the swapping. So it identifies that which memory blocks are not frequently used, and those blocks can be put onto the disk, and the blocks which are frequently used, they will be placed in the regular RAM, so that you have a faster access to those memory module, right? So that is one of the important function of the memory management module. Also, another thing we have seen that you have a data memory, you have program memory, right? You have a heap, you have a stack, all of those different kinds of memories you have, right? So which part of your physical memory will be divided into each of those segments? That is also one of the function of memory management model. Okay, so all these functionalities are to be performed by the memory management. Then you have the file system module where we manage what we call block devices. So when we talk about the device drivers, they generally deal with three types of devices. One is the character device, second one is the block device, third one is the network device. Okay, this somebody unmuted. And because the mic is right here, it's echoing back. So character device, block device, network device, CDs, USBs, DVDs, all of these are block device. Okay, your keyboard, display, those devices are, so generally console-based devices are your character-based device, and then you have the network ports, which is Bluetooth, your Ethernet, and all of that. Right, that will be your network device. So this module basically deals with only file system, which is either it can be on the USB drive, it can be on the DVD or DVD CD or your disks, regular disks, right? Hard drives. Yeah.
Is there device driver is for each and every hardware component?
Correct. Every single hardware component that you have in your system, for each one of them, there will be a separate driver.
Even for CPU?
So for CPU, you have this process management module, which will have different components that will say that how the allocation of the task or the application should be done to a particular CPU. And remember, I told you that when you have a large I/O activity that happens in your application, then that process will go into a sleep mode. So all of that scheduling part is a special code that is in the kernel, and that takes care of all of that. So device driver, specifically, we generally use the term device driver mainly for I/O devices, input-output devices, not generally for CPU, right? So, I mean, when you have file system, when you have the keyboard, mouse, all of those devices, we generally call it as device driver, right? For the memory system, for the process management or CPU management, generally we don't call it as device driver because device means your I/O devices. Okay. Yeah. The block devices are, like I said, anything where you write or read a block of data at a time. So this can be, your disk drive can be a block device, your USB drive can be a block device. So anything where you write data not in a single byte but multiple bytes at a time, that is what we call block device. So I'll come to that actually in the next slide. But so then you have the TTYs, which stands for teletype devices, and they are primarily your keyboards, displays, and all that. They are your character devices, right? So single byte, single character at a time that you would read and write from those devices. And then finally, you have the networking subsystem, which is interfacing with the network devices. So generally, these type of resources your system has to manage, and for each of these, you will have a separate module. Okay, as I said, three types of devices generally we deal with. Character device, which is your console, keyboard, mouse, etc. Now, of course, if your mouse is USB mouse, then you will have the USB device driver, which will be managing the mouse. Then you have the block devices. So the difference primarily between the character device and the block device is that only single process will be allowed to use your character device, in the sense that only one process can read and write from the keyboard and the screen. right? Not multiple devices, multiple applications cannot access that device. But when we talk about the block device, multiple applications can access the block devices. So for example, USB drives can be used by multiple applications at the same time, right? But not the keyboard. Okay. And then you have the network device, which are like Ethernet card or Bluetooth or something like that. Now, what we will do through this chapter is, I've provided this link. If you are interested in this particular topic to learn in detail, go through this link. This is basically a book link. It's about 20, I think 20 odd chapters book. The device driver actually is a very big topic. So I won't be able to cover like complete topic here, but we'll create a small device driver for a character device, which is generally covered, I think, in chapter 2 and 3 in the book. Then they have covered many other device drivers like USB device drivers. For the other types of devices also, they have covered some of the drivers. So if you are interested in that, you can dig more into it and learn more into it. But this chapter is primarily again to give you the introduction about how do we create a simple device driver, right? So when you create the device driver, we need to define certain information in our module. By the way, device driver belongs to the kernel area, right? So whatever code that we will implement will not actually have an executable file. You don't run an executable for a device driver. Device driver will have a special type of object code or a binary code, which will be like kernel module. Okay. So we don't have a main function here in the device driver because all of the programs will have the main function, generally speaking, right? But here we will not have the main function. We will provide the licensing information, author information, module description, and then the version, right? So these four information you can provide by using special macros that are defined by the kernel: module license, module author, module description, and module version. So these four macros we can use to define this four information. Now, as I said, the device driver code is actually part of kernel or will have to be part of the kernel. And so we don't actually have the main function for it because we don't run an executable. So what the operating system allows us to do is that we can define our own init function, right, or initialization function, where you can declare your global variables or create your heap variables or anything like that, initialization and things like that, which we can call it as constructor, right? And you use this special system call called module init, which is where you will provide the address of the init function that you have created in your code. Okay, so by providing the function name here, primarily what we are doing is we are telling the kernel what is the name of the init module or what is the address of the init module that we have written in our code, so that when the device driver is loaded into the memory, that is the first function that the kernel will execute for the driver. Okay, because we don't have the main function, right? There is no main function. So because there is no main function, there has to be some starting point, right? So what is the starting point in the device driver? The starting point is the init function which I have created, and I have told kernel, which function to start from. Okay, so that is what this init module init does. Similarly, we can create an exit function of our own, and then we tell the kernel what is our exit function. So let's say you have used global variable called something, and then you've done malloc, right? So are you guys familiar with malloc? Yes. So what does malloc do? Malloc creates a global variable which is a memory space allocated in the heap, right? Heap is a special memory which keeps track of all the global variables. Okay, so when you have the variable created in the heap, once you're done with your application, you need to free up all the space, right? Because you cannot just go away from the application and keep the memory allocated, right? Why is that? Because at some point, what will happen is you will take up all the memory in your computer and your computer will freeze. The only way to recover from that is to reboot the system. Okay, and this problem that I'm describing is what is called memory leak. Okay, so if you Google it up, you will find out that this is a common problem, especially when you write a code with the lower level languages like C, where you can allocate memory on your own and use pointers, right? So you end up having memory leaks if you don't manage the memory well. This is one of the main reason other languages such as Java, Python, they don't allow you to do memory management on your own. They do memory management for you, okay, so that they fix all of these memory leak problem for you. They don't allow you to touch the heap. That is what they do, right? But anyway, this is also one of the reasons that these languages cannot be used in kernel programming. Okay. Now when we use your normal application in C, we use printf statements, right? Just to print the certain messages. So here, because this is a kernel module, we cannot use printf, but we have to use printk. So printk is again a special function which will allow you to print messages, but then you can also provide the log level or the priority of the messages, right? So what kind of message that you are displaying? Is it a debug information, informational message, error, warning, critical error, whatever it is, right? So you can provide this information. This sort of information goes into the log, and a special log. Again, when we look at the example, you will notice that this information goes into the special log, and you can take corrective actions based on this log information. Okay. So too much talk. Right, 6 slides. Now 7th slide, we go with a simple example. Okay, so we want to see how the kernel modules are created. So even though I have said driver 1, it's not actually, this code does not actually do anything, or it doesn't have any device driver related code. Okay, I will go through like 5 different examples, and in each example we will have an incremental modification to the code. The last example, the 5th example, is the real driver code, okay, which is what actually the driver is, right? All the other code is just to show you the incremental changes that we can do to build the device driver, right? Okay. So simple code here, my driver 1. These are the header files that we will need, and if you see, it is in the Linux directory, okay. And we are using the header files from the kernel modules. So all of these header files are actually coming from the source of the kernel, okay? And therefore, the compilation process for this module is also slightly different, which I'll explain through the make file. But for now, we have to declare our init function, right? So this is my init function, and I'm just putting these 2 print case. It's just informational messages. It's just saying that it's a simple module and the module is inserted. And then in the exit function, again, we are just saying that the module is removed, so that we know that when the module is loaded and when the module is removed. And then these are these 2 module init and module exit system calls, which is then defining what is my init function and what is my exit function for the kernel to execute, right? And then these are the 4 macros that I've used for defining the license, author, description, and version. Okay. So you can see that this code doesn't have our normal, flow, right? It doesn't have main, it doesn't have function calls, it doesn't have anything like that. Okay. It's just these 2 simple functions which are there. Now, how do we compile this code? Right. So in order to compile this code, we write this special make file, okay, and this make file is actually, it's a recursive make file, in the sense that this make file will be calling a make file from the kernel code, and that make file will be again calling this make file to compile our code. Okay, so that's why we are calling recursive. So basically this make file is called twice. One when we execute, second time when kernel calls this make file. Okay, and how does it work? So basically, if you see that there is a variable here which I am using called kernel release. Okay, and this is an if statement that is checking whether the kernel release variable is set or not. Okay, whether the value in the kernel release variable is set or not. That is what this if condition is checking. In the first time when I execute this make file, the kernel release variable is not set. Okay, so it's going to go and go to the else part. It's going to declare this initialize this variable kernel directory, and if you see, this is the path to the kernel directory. Okay, if you see this part in the middle, this is trying to get what is the current kernel version that I am running, because I could have multiple kernel versions sitting on my system, right? But which kernel version I have booted from, that is the kernel version I need to use here. So uname minus R is going to give me the current booted kernel version. Okay, so that is what I'm going to replace here. Okay, so it's going to go to lib modules, the kernel version, and the build, this folder. Okay, and that is where I have a make file, which is the kernel's make file. Okay, and then I'm going to set what is my current path, right? So that when the kernel makefile needs to call this makefile, it knows where my makefile is. Okay, so I'm going to call the makefile in the kernel directory, and then that makefile is going to call this makefile again. Okay, so this is the make command that I'm executing, and this make command is going to run in a kernel directory because I'm saying -c switch. So if you look at the man page for make, okay, so -c switch, you provide the directory, and it says that change to that directory before reading the make file or doing anything else. Okay, what does it mean? It means that you first go to that directory and then run the make file from that directory. That is what you're trying to do, right? So now that directory is what? It is this one, right? Because we are providing the kernel directory as the path for that -c switch. Okay, so it's going to go to this directory. Okay, and if I do uname -r, this is my current kernel version that I am currently running. Okay, so what I'll do is I'll go to that particular folder. So I go to other locations, here, lib modules, and then I look for that version number. I think it was this one, 37, and then build, and then in this build there is a make file here. Okay, so this is the make file that I will be executing. Okay, this is the make file I will be executing, and if you see, the make file is about 1794 lines. So obviously I will not have time to explain all the commands there, but what you have to believe me is that we are running the label modules. If you look at our make file, right? If you look at our make file, there is a modules word here, right? So this is the label which I am executing from that make file, right? So if you look at this make file, there is a modules label here. So this is the part of makefile which I am executing. And if you dig down a little bit, if you're interested, you can dig down on this makefile.modepos. Eventually, it comes back to our makefile. Okay, that makefile executes our makefile. But when it executes the makefile, the kernel release variable is now set. Okay, so kernel release variable will be set inside this makefile, and that is what is going to be used for the if part here. So now next time when this makefile is called, this variable is set, and because this variable is set, I am going to set obj minus m variable, and I'm going to say what is the object file I want to create. Again, it is going to call this makefile, but this time it is going to compile my code. So basically, there is two times the kernel makefiles is being called, and two times my makefile is going. This makefile is being called to compile the code. Okay, that is what is happening, and this is the only way to compile a device driver code using the kernel makefile. So this is a standard makefile which most of the, even if you create your own system calls, for example, if you create your own system call which you want to include in the kernel, same makefile you will have to use. So any kernel module you want to compile, any new code that you want to include in the kernel, this is the makefile that you will be using. Okay. Any questions? Okay. So let me first compile the code. Now, one important thing that you have to note is that because this is a kernel code and we require access to the header file, which are the kernel header files, we cannot compile this code in this folder, because this folder is the mapped folder or mounted folder from the Windows file system. Windows file system does not have the Linux header files. Okay, so whenever you want to compile any kernel level code, you have to copy that code into the local file system, in the Linux file system, and that is where you will have to compile. Okay, so what I'll do is actually I'll go to the home folder. There I have created the device driver folder, and I've copied the C files and the make files over here. Okay, so that we can actually compile here. So I'll just copy the my driver one makefile to makefile. Okay, so now makefile will look like the one that I want to execute. And so I'll say first let me just clean in case if there are any ports which are created. So I'll first do the clean and then I will compile. Okay. So when you compile, you will notice that there are several files that are created, and if you look at the output, I'll point out a couple of things. One thing is that if you see in the makefile, these are the three variables which we are printing. Okay, make variable we are printing, pwd we are printing, and kernel release we are printing. Okay. Now I said that this makefile is being called twice, and I can prove to you that the way I can prove it, because if you see, those three variables are printed here first, right? And if you see the kernel release, it doesn't have any value, right? It is, and then there is nothing. Okay, and then it does call the kernel code, right? Somewhere here, this is the kernel code. Kernel makefile will be called here, and then that kernel makefile is again calling our makefile, and so it is displaying the same three variables again, second time, right? So when it is doing that, you will see that the kernel release variable is having a value now, because this variable was set inside this makefile, which is what we call from the kernel side. Okay. So once we have this variable declared or initialized with this kernel version number, now the else part will start running, and now we are creating this object file. So this is the second time that kernel makefile is being called, and then again the third time our makefile is called, and then finally all the compilation is happening here. So there's like back and forth going 2-3 times, right, between the makefile of the kernel and the makefile that we have created, and then finally the object file gets created. And if you look at this makefile dot mode post, it actually gives you the steps. It gives you the steps that why these 4 files are being created. It has the comments there, which you can read if you are interested. But in short, we are primarily interested in this object file, a .ko file. So that .ko is the extension for kernel object, right? So normally we create a .o file, which is the object file, which is the binary code, compiled code of the C file. But because we are compiling a kernel object, right? The header files that we are using is from the kernel side. It's going to create a .ko file, and that is what we will use as our binary file. And that is what we will have to load it into the memory for drivers, right, or device drivers. Okay. So how do we load that? Right now, this is a .ko file. I cannot really run it as an executable. So how do we load that? So we have command called ins mode. Ins mode is the command that basically says insert module, and we provide the .ko file to that, which will be then loading that .ko file into the memory. ls mod stands for module, right? So ls mod basically gives you the list of all the modules which are currently loaded, meaning all the device drivers that are currently loaded, whatever is running right now, right? And then rm mode is what we can use to remove the module. Okay. Print k messages are going to a special log, as I was saying. So if you want to list those, how would you see the messages from that log? Dmessage is the command for that. Okay. So we can't really see that those messages on the console, on the screen, because those are going to the special log on the system side. Okay. So you can use dmessage for displaying that message. So let us first look at all the modules which are loaded. So these are all the drivers which are already running on the system. Okay. And if I do ls mod grep my driver 1, you won't find anything because it's not loaded right now. Right? So I need to load it. In order to load, I need to be a super user. Okay. Now if I run my ls, then it says that the module is loaded. Okay. Now how do I know? There's another way to check it, whether the module is loaded or not. If I run the message, you will see that the last 2 lines are coming from that special log, right? And these are the 2 print case I've done in my init function. So that means when the module is loaded, the kernel has executed the init function, right? The init function that I wrote in my code. Okay, so this is how I know that the module is loaded into the memory. Okay, now of course this module doesn't do anything, right? So I can just remove it because it just has init and exit function. That's all, right? So there is really no driver as such. There is no device as such here. It's just that this example is just showing you how to create a kernel object and load it into the memory. That's all. So I'll remove it. Again, if we do ls, it's gone. And if we do remessage, you will notice that the kernel module is removed successfully. So that means the exit function is now executed. Okay, so when you load the module, the init function is executed by kernel. When you remove the module, the exit function will be, sorry, init initially and then the exit when you exit the code. Okay. So this is how your modules can be started off for writing the device driver. Right? Just a very simple code, just to show you how to load module, remove the module. That's all. Any questions? Clear, everyone? Okay. Yeah. How are? So that's what I'm saying. It's not executed. It's executed by kernel, right? So when you write the code and when you load it into the memory already has the code, right? The kernel knows where the module is loaded. So when you try to use it, kernel knows, and you are not directly calling the module. You are calling the kernel system call. Right? So when you call the kernel system call, this is so. What I'm saying is that if you wait till example 5, you will get all your answers. So wait till example 5, please. It's an incremental. See, I can show you a example 5 in the first shot itself, but then it will be difficult for you to make heads and tails out of it, right? So for example, this is like, so if I explain to you this now, it won't be easy for you, right? So what I'm doing is I'm going through incremental changes, so one step at a time, right? Better way to learn is one step at a time, right? So I know your generation is faster and you want to do everything faster, but sometimes you got to take, that halt. Otherwise, you will burn out. Sorry? No, no, I understand that. And I'm sure that, many students have the same questions in their mind. So let me stop here, because the next part I'll take probably 15 minutes, 20 minutes more. Yeah. Yes. So basically, what happens is that the kernel makefile is called twice, and then the third time the kernel makefile is calling our file to compile the code. So last call to our makefile is compilation. The first two is just to generate the messages. It's just to collect the data. So first time that kernel dir will be set, second time that objm will be set, and third time the actual compilation will happen.